So OLS regression is one of the most popular statistical techniques in existence. Okay, so many people use OLS regression. You can use all sorts of software programs to estimate OLS models. You can use programs such as Stata, SAS, SPSS, or R. What I have here is output from R. Regardless of how popular it is, I found that people from all walks of life, they run an OLS regression model and they're not quite sure what the output means. I mean, look at that. It's not a pretty picture, right? So what I want to do in this video is give you the top 3 things that I look for when I'm looking at an OLS regression table. Okay, so let me explain what this table is in this context. So what we're doing is we're running a regression to figure out home prices, all right, to try to predict home prices. And we say that there are 3 variables that are important: square footage, bathrooms, the number of bathrooms, and the distance in miles from the center of a city. So what we're going to do here is we're going to run this regression and we're going to get output like this. So let's go through it. The first thing that we're going to look at are the coefficient estimates. Okay, so coefficient estimates tell us how much each independent variable influences the dependent variable while holding the other ones constant. So you can think of these as slopes. So square feet, you'll see the coefficient estimate is 46.572. That's simply a slope saying if there was a 1 unit change in square feet, you would see a 46.572 change in the price of the home. Okay, so you can think of it this way. These are simply slopes. You can think about your calculus classes that you took, or your algebra classes that you took when you were in high school, or maybe you're taking them in college. And a slope just tells you how much the y changes as a function of the x. So in this example, you can see that the influence of square footage on price is positive, and it's 46.57, which I just said earlier. The home price is on the vertical axis, square footage on the horizontal axis. We can also look at the number of bathrooms, and you can see what happens. As we add bathrooms, the price of the home goes up. Okay, and the slope here is 9,415. So adding an additional bathroom adds $9,415 to the price of the home. And then finally, we have distance from downtown. Okay, and you'll see that the slope here is negative 919 per mile. Okay, so as you get further away from the center of downtown, the prices get lower. So this shows an important point that coefficients can be positive or negative. Okay, so they can positively influence the dependent variable of interest, or they can negatively influence the dependent variable of interest. Now, after that, we're going to look at p-values. Okay, so we have these estimates. The question is, what is the statistical significance of these results? Now, there are entire literatures on p-values and how complicated they are to interpret. So what I will say is this. I think about this as, would we find this by chance? What are the chances that we would find this result just by chance? Okay, and we're looking for lower p-values. And so as you'll see here, all of these p-values, you'll see one associated with each coefficient, okay, is less than 0.05. So this ranges from 0 to 1. It's a percent, okay? So there is less than a 5% chance that we'd find these by chance, okay? So this gives us evidence that these relationships actually exist. So we want to see statistical significance. Again, I could talk a lot more about p-values. I don't want to get into them right now, but I think that simple rule of thumb can help you. So we're looking for low p-values just to rule out that our results are strictly due to chance. Okay, and you'll see these asterisks next, or asterisks next to the results. So there's 1 star, meaning it's less than 0.05. The more stars you get, the more statistically significant it is. All right, which leads us to our third statistic, and that is R squared. And this one is really important, and not many people think about this, and I'd like for people to think about this more. R squared tells you how well your model helps explain the dependent variable of interest. This also ranges from 0 to 1, except in this case, we want the value to be as high as possible. So in this example, we have an R squared value of 0.136. So this means that the three variables in our model explain 13.6% of the variance or the variation in the dependent variable. So one way to think about this is to visualize it. Now, some people can put up a pie chart, which is fairly easy to understand. But in this example, let's use a house. Okay, so in this example, we can see that our variables explained 13.6% of the variation in home prices. And that's represented by the green portion of the house. If you look at the other portion of the house, which is some sort of red or orange, I'm not exactly sure, it's 86.4%. And that is unexplained variation in home prices. So that means other variables out there explain that we haven't measured, explain the rest of the variation in home prices. So in this example, again, we've only explained about 13 or 14% of the variation in home prices. So in sum, there are really three things that I look for first when I look at a regression table: the coefficient estimates, the statistical significance of the estimates, and then the R-squared. The R-squared tells us how important these estimates are for explaining why. It's quite possible we can have statistically significant results, but the R-squared is only 1%. That's not a great model. So you have to look at all of these three together. But when you do, you can understand that OLS is a very powerful statistical tool.